start. Sorry. So I said that I'm very proud to be here, very happy to be here, because it's a way to remember Nicolas Cabrera, who now gives the name to this department. And and Cabrera is at the beginning of the story of the helium atom scattering, the theory, together with Vittorio Celli, who is represented there, the second person in the circle. And Cabrera was in 1970, in those years, late 60s, early 70s, he was in Virginia, in Charlottesville, working together with Vittorio Celli, and a very good student, a PhD student, was Dick Manson. And Dick Manson was not here at this school, but because Cabrera was already in Madrid, and it took some of his co-workers here. You may recognize in the third circle, you may recognize, do you recognize him? Probably not, because he has a beard. He was in Barbados at that time, and you don't recognize him? Javier Solana, of course. Oh, Javier Solana was there, you know, as a physicist, and he was there. And I also was in Barbados at that time, because it was fashionable to have a long beard, not long, but a beard at least. And I was very proud, because it actually was the first time, the only time where I was a lecturer, and Peter Tönnies was a student there. Actually, was not a student; he was already just a director of the Max Planck Institute in Göttingen. But he came as a student to learn how it would be possible to detect surface phonons, surface dynamics, with helium atom scattering. So he was thinking of the experiment at that time. And okay, there were also very interesting personalities there, like Bob Schrieffer, that at that time had some interest for surface physics. Probably he was dreaming of surface superconductors, which came much later, however. And this was the, okay, this was 1973. Now, so this is the title of the talk today, which is Fishing for Bosons in the Fermi Sea. And the reason, well, what does this mean? Well, you will understand soon what does it mean, fishing for bosons in the Fermi Sea. And this is actually, I'm speaking about very many collaborations that I had during the years, of course, with Peter Tönnies, Daniel and his group, Wolfgang Ernst in Graz with his group, Bill Ellison in Cambridge with his group, and Dick Manson, Salvador Miretartes, and my group, my former group in Milano, Marco Bernasconi, Davide Campi, and of course in San Sebastian at the IPC with Eugenia Chulkov, Pedro Echenique, and company. Okay, this is the story. So the story of the helium atom scattering, of course, is started much earlier. You recognize this man, maybe. Sorry for the test today, but this is a bit more difficult. This is Otto Stern, and he's very famous for his cigar, actually, because this is the cigar which permitted him to be successful in the famous Stern-Gerlach experiment. But it was also very important because in 1929 he made an experiment with helium atom scattering of thermal helium from a surface of sodium chloride. He calculated that if quantum mechanics works, then it should have a lambda wavelength which is comparable with the distances of interatomic distances in atoms. The distances they knew at the time already. So, but he made a famous experiment And so, in fact, the diffraction, of course, the diffraction was there was a specular peak and two very broad peaks, but this was a proof that the atoms were behaving as quantum objects. Great. But I say two needs for one deed, because these experiments not only proved the quantum mechanics made with atoms, but also the crystallographic structure, the crystallography of the surface. And so this was very important. But today we would say that the needs which have been fulfilled are at least 5. The major progress was with the invention of supersonic sources of atoms, where the speed ratio can be fantastic. It depends on the pressure. And the speed ratio, which is supersonic, how much? Which is the Mach number? Well, the Mach number can be 100, can be 100, up to 200. So with a fantastic resolution in energy, they become extremely narrow, and so the speed ratio can be thousands. Speed ratio means the speed of the atoms in respect to the means the relative temperature they have in the beam when they are monochromatic. So the relative temperature in the beam is in the millikelvin. So the beam is by itself very cold, millikelvin, with respect to the speed that the beam itself has. So this can be the thousands. Okay, and this turn has made this progress, and the change, the nature of this program. This problem here is from here to here. This is the diffraction of a sodium fluoride surface made by one of the first experiments by Turnus. This tells you at room temperature. This tells you the progress in the resolution. Okay. I don't know. I keep pushing and nothing happens here anymore. So now the original ideas was with insulators that you have a collision of an atom with the surface atom. So it's a two-body collisions. And so the first formulation of this was, as I say, Cabrera, Manson, and Celli. This was it was based on the classical theory of scattering, in which you have, well, classical in the sense that it was used, but it's quantum, of course. And here you have the reflection, differential reflection coefficient is produced by inelastic scattering of phonons, is proportional to some forces which acts on the atom directly in the collision, times the response of the system, which is represented by the imaginary part of the Green's function, which bears the information on the dynamics of the surface. So what's happening here? That doesn't work. Okay. So this is in the Green's function, which is a correlation function of the displacements of the atom. So displacement correlation function. You see that is just this zero, displacement at zero means at the first layer. So just as the atoms move at the first layer, because you say, okay, it's a collision, atom-atom collision, we only are interested in what happens at the first layer. This was and then you have ingredients which you know, initial energy of the atom, final energy of the atoms, phonon energy, which is h bar omega, and this is the response function. It looks very simple. You just have to model the forces. That's all. Okay. But as soon as you made this experiment on metals, you had a surprise. Because in metals, this is a typical time-of-flight spectra taken from copper surface. The surprise was that you have a peak. The first peak you see is the largest peak is the elastic peak. Is the elastic, but then you have the inelastic peaks, and the first peak you see is the is the Rayleigh wave, what was known to be the most important vibrations at the surface. Is an acoustic wave, which is below the spectrum of the bulk, and therefore is something that is localized at the surface, and it must be visible in these experiments. And it was the case. This was fantastic. It was a peak, a sharp peak, but it was something else. It was another peak. And when you go on the right side of this picture, you see that the second peak becomes larger than the Rayleigh wave peak. And this came as a surprise. What is that? What is that? This was called at the time anomalous longitudinal resonance because it had the dispersion of a acoustic mode, but it was below the threshold of the longitudinal. And so it was called longitudinal resonance. You see now the two dispersion curves, and this is the broken line. The upper one broken line is the longitudinal bulk mode, but it's below, quite below, and it gets quite softened at the border of the zone. The other surprise was this existing in all metals. All metals have this special surface phonons, which was not expected. So this was the first surprise of this kind of spectroscopy. No chance. No chance. Now, the story now brings in the explanation of the bones and the skin. What does it mean? Well, the question was, why the longitudinal resonance is so soft, is our boundary. The second, why is it observed at all? Why it is found in all metal surfaces? This was the question at the time. And at that time, I'm sorry, but I like to make cartoons, so I like to show this. So we were in Göttingen at that time. You recognized me with the beard, and then Vittorio Celli and Peter. And Vittorio called a theoretician who now unfortunately passed away a few years ago, which is Bortolani, Eugenio Bortolani in Modena. He was the Pope of dynamics of metals at that time and was doing a surface dynamics of metals. And he was trying to understand these new experiments, and he did not succeed. Then we called, he just started drinking Lambrusco because he didn't know how to solve the problem, but we called him overnight. And so he said, look, is the story of the bones and the skins. You have to understand, what does it mean? Well, we explain you immediately. Not so immediately because it doesn't work, but what can I do? Let's go in this way. Seguente. Okay, it's much faster. Now, the bones of the skin is the following. The surface of a metal is covered by a surface charge density of electrons, conduction electrons, and atoms who scatter from the surface cannot approach the surface, thermal atoms, cannot approach the surface for shorter than less than 3 Armstrong away. So they are away from, they do not see the atoms. They do not see the atoms at all. So how they can transmit, how they can create phonons? How do they transmit the energy to phonons? So the answer is obvious, through the electron-phonon interaction, through G. They move the electrons, and the electrons move the atoms. Fantastic. So helium atoms are a direct probe of the electron-phonon interaction, at the surface at least. So this was actually, we wanted to prove that. So we started doing calculations. First principle calculation, that was done already in much later, much later, in the LPC. And the surprise was we calculated the dispersion curves from first principle, but what is shown here is not the vibrational amplitude, but is the amplitude of the surface density oscillations. So the surface charge density. And the surprise is that the strongest mode is, if you look for example, SV2, which means phonons with the shear vertical vibrations of the atoms perpendicular to the surface, but on the second layer. Okay, on the left, you have first layer, and you see only the Rayleigh wave, which is important. But when you go to the second layer, you see that the most important is S3. And S3 is what is called the longitudinal resonance. Fantastic, but it's on the second layer. How it happens that if I move the atoms in the second layer, I see oscillations of the charge? Well, this is life. This is the electron-phonon interaction. Okay, you also see the optical modes, S2. This S2 optical surface modes. There's no optical mode in copper, but in the surface there are optical modes. And you see also the branches, which are called S2. Fantastic. So now we understand the spectra. But we discovered that these modes are not at the surface, are below. Let's make a calculation of the charge density oscillations. Now inside the crystal. And we see fantastic that here below S2, we move only the atoms in the second and the third row. The largest displacement in the third row, but we see the modes, we see oscillations of the charge, the surface. Red means up, blue means down. The charge is moving. We also explain something which has been published on Nature, not by ourselves, but by Gavronsky people. They did jets, they did with the STM, inelastic STM, no? And they measured very nice measurements. They published on Science, and they saw a fantastic mode at 20 for copper 111. And they said, oh gosh, but this is not corresponding to the Rayleigh wave. So they were start arguing why maybe the Rayleigh wave is stiffer at the zone boundary and so on. No, this was not explanation. Explanation was very simple. With the X, you have the same effect. You see the oscillations of charge. You don't see the oscillation of atoms. You see indirectly, and there because you modulate the barrier in STM, and therefore you see the modes which have the largest electron-phonon interaction. You don't see the Rayleigh wave. You see S3. So this was another example of original misunderstanding, which, however, led to an important fact. No. Okay, this is the story. Now, no, I better use the other way. This doesn't work. Siguiente. Okay, we have another fantastic example from here. This is graphene on ruthenium, which has been measured by Daniel and Macaniello, and etc. I think also Amjad was involved here. Yes, and this you see here the moire of pattern of graphene on ruthenium, but the interesting point is that here you have a graphene on top, but in the dispersion curve you see the lowest branch, not the end, which is the moire, but the lowest branch, which is termed Rayleigh wave RW ruthenium. What? Do you see the Rayleigh wave of ruthenium even at the zone boundary? What's that? It's impossible because at the zone boundary, the layer of graphene is perfectly immobile. Why that? Because he cannot, if he has to move with such a short wavelength, it must be, it's very high, it's 40 milliV. So it cannot move simply. The ruthenium is oscillating beneath an immobile surface. And why do you observe that? Well, the surface is immobile, but the electrons, which are transferred to graphene, are moving up and down. And this is what you see. This is why you see the Rayleigh wave. Well, there is another mystery here, which is not yet solved, is the mode S7. This mode S7, nobody knows. We don't know what it is. We suspect that it's in electronic excitations. But okay. Does it exist, that mode? As vibrations. Okay. So the story is getting more interesting. No, sorry, siguiente and siguiente. Okay. You became more interested when you started putting 1 layer, 2 layer, 3 layer, 4 layer of lead. Lead is superconductor and remains superconducting even when there is 1 layer on single layer on silicon, for example. Now here the experiments was put. This was on copper, which was easier. It was done in Göttingen many years ago. And the surprise is that the more layer you put, the more phonons you observe. You see, with only 4 layers, you have 1, 2, 3, 4, 5, perhaps 6 branches observed within the scale. Cannot be just a wave, of course. You see the peaks, the elastic peak, and then you see many phonons. And you see the scan curve is the green curve. The intersections correspond to the phonons that are observed in that figure, in the time of flight figure, energy transfer figure. How many phonons? But the surprise is that when you make the calculation of that, this is the first principle calculation, you discover that the epsilon 2, the branch, is a motion at the interface, not at the surface. And you do observe that. It's a nice peaks. Well, you go to 7 layer, you see a fantastic collection of phonons. Even the highest one, epsilon 2, which is at the interface. So it's 7 layers deep. And you see that. So is helium scattering a pure surface probe? Not quite. You can probe as deep as the electron-phonon interaction range. If the electron-phonon interaction range is long, you know it may be long because you have Friedel oscillations. You see that. So this is very, very interesting because it's a semi-surface probe. Right? You can see in metals, of course. Good. Here you have different time of flight up to 8, and you keep seeing the guys at 10 milliV next to 10 9 milliV, which are the famous epsilon 2 modes, the largest one, the interface mode. So, okay, this tells you the story. The first principle calculation confirms this observation. And that we coined the terms the quantum sonar effect. So the helium scattering works as a sort of quantum sonar, and this is the way we fish phonons deep in the Fermi sea. Because we need the Fermi sea, of course. If you don't have the Fermi sea, you cannot fish. So this is the point. Okay, this is the story. And this is the diagram, which explains you in a Feynman language, which explains that you have an interaction there through the matrix elements of the non-diagonal density matrix, density of the electrons. So you have 2 wave functions, and below you have the electron-phonon interaction, which transforms the whole electron pair into a phonon. And this is the way you can create phonons deep. Depends on the depth of the electron-phonon interaction. Okay, so the electron-phonon interaction had to, the theory had to be reformulated in terms of matrix elements of the potential of the surface produced by the electron density. And this was written in the way, for example, in the Norskov-Esbjerg way, which is just proportional to the density. To the density, time-dependent density, of course, at a position, different position. And therefore, when you take this matrix element from, you have this kind of elements, where kind of formula where G is the electron-phonon interaction matrix, the way we know. And this, of course, in principle, can be applied to metals, but to any systems where where there is a polarizability, where there is a susceptibility. So even insulators, we have a polarizability of the ions, of the atoms, or in semiconductors, you have a bond charges which may be displaced and so on. So in principle, but we only applied and consider so far only metals for conducting surfaces. Let me put the seguente. Okay, so this is the elements of the electron act as effective inelastic scattering potential. And this is the approach. And this is the electron-phonon interaction matrix, as I said. And this, you may recognize that expression is essentially the electron susceptibility. I wrote something more below, because you see that chi0 is the electron susceptibility, the way you use in the Lambda form and so on. But I added the Coulomb interaction among electrons. And so you have the denominator, 1 minus something. And this, you recognize the Fourier transform of the Coulomb interaction among electrons. And therefore, in principle, in that denominator gives also collective excitations of electrons, not just single particle electron, but collective. So, in principle, plasmons. Of course, they must have very low energy plasma, because with helium-atom scatter you cannot go much higher. But, for example, acoustic plasmas, they also can be, now we know that can be seen with helium-atom scatter. Okay, there was a paper with one of the last papers we did together, no? So, okay, so this is the story, and so this is and now, when you work with this electron-phonon interaction matrix times the matrix elements, then you can reduce that to an expression, approximate expression, where you have the lambda q, which is the electron-phonon interaction specific for that mode, for the phonon mode of wave vector q, parallel wave vector, and new branch index. This is also called a mode-selected electron-phonon coupling. Luckily, this f is a slowly varying function, which is also known, if you wish, and is the density of the electronic states at the Fermi level. So this is very convenient, because you see that the reflection coefficients is a sum of delta functions over the different phonons, and they are weighted by the electron-phonon interaction. So the amplitude, this was the first principle calculation of the lambda specific. This, I don't want to comment on this for the different cases, 3-5 layers of lead on. But I want to go a bit further and show this, because the first principle calculated lambda for the different phonons, which are met in this particular configuration of the scattering, are in quite good agreement with what you see with helium-atom scattering. So helium-atom scattering is practically, apart some constant, is measuring, some quasi-constant is measuring the electron-phonon interaction of specific phonons, proportionally, of course. This was a specific calculation of the puzzle. You see that first principle calculation agrees fairly well with the case of lead fields. And so this was the conclusions of this study, and what we call lambda spectroscopy. Okay, this is the interesting case of lead, where when you put on silicon, the superconductivity is persistent down to 4 layers, and then it drops. The temperature drops down. It is still superconductor at 1 layer, single layer, but it's between 1 and 2 Kelvin. The temperature drops dramatically 3. And the interesting point is that at 3 layers, you don't have the famous epsilon 2 mode. It disappears. So we suspect that this mode is the culprit. The culprit is the one which provides the largest electron-phonon interaction. So, just suspicion, nothing more than that. Because, this is the interesting case. Okay. Then the other step, well, this was actually the idea of Dick Manson. Can we measure the Debye-Waller the lambda, the total lambda, not the total lambda is an average over all the individual lambda. Can we measure that? This is very interesting because when you want to calculate the superconducting temperature, you use the Macmillan formula to have an idea. You put lambda inside of that. No, you need other things, but you need lambda. You need the phonon frequency and so on, the Coulomb interaction, the mu star. But lambda is the main ingredient. Okay. So the question is, since the Debye-Waller factor is a measure of the mean square displacement of the atoms in normal scattering. In you know, Debye-Waller. I met also Waller. I met him. It was very old, 1977. Yes, and he was a student of Debye, and he developed this theory for X scattering. Of course, X scattering is a collision directly on the cores, and so what you need is the mean square displacement of the cores of the atoms. And also in atoms, if you have a collision atom against atoms, you need a Debye-Waller factor. You need a mean square displacement of the atoms. Okay, but here in metals you don't see atoms. You see the motion of the charge. So the Debye-Waller is bearing another piece of information, which is not the mean square displacement of the atoms, but is something which is proportional to them. Proportional through what? Through the electron-phonon interaction. Which one? Well, in the Debye-Waller mean square displacement, you have all phonons contributing. Okay, so maybe it is the average of all the phonons. So maybe it's lambda. Maybe. You have to make some approximations, which Fernando is now arguing about the many approximation. I think it's maybe true. Maybe true, of course. You know, it's always a working. The work is always in progress. This is the point. Okay, so actually we worked out this. We started showing that, in fact, this W effective is something as the mean square displacement or something related to that of the phonons. You see the population of phonons plus 1/2, but you also have lambda involved now. They are weighted that way. Okay, this was the way we expressed that. You have the density of electron states at the Fermi level, and so on, the effective mass of the electrons, and so on. And also, you also have phi. This is another critical point, which is the work function. And the reason why that the work function tells you gives you an information on how does the charge density decay away from the surface. Why that? Because this is what you atoms meet. So you have to know how does the density of electrons falls down. And this through certain approaches, you find that at the end you end with this information. So as I say, lambda is the average of this lambda. And so after various manipulations, we got this expression for lambda by making this average. And you have a certain advantage in working when the temperature is high, so that the population becomes a linear function. I mean, as a linear decay, and therefore everything becomes simpler. So you just divide by the temperature which you're measuring. And is it true? So we started examining simple methods, cesium layers on all data, which however were revived on copper, and you see that using this formatted, this simplified expression, where we discovered that there is a saturation number, a number which gives you the range of the electron-phonon interaction, in the sense that if you measure 1 layer, 2 layer, 3 layer, you see that alpha there increases linearly, but then saturates to certain values. It becomes, and this was, you see that you have the slopes of the Debye-Waller factor for 1, 2, 3, 4 layers, at 10 layers, then at 10 it becomes saturated. So, of course, if you go to the semi-infinite crystal limit, but you can only explore certain size of this. Of course, here is so if you go to okay, if you go to two-dimensional materials or topological insulators, because we have measurements done in graphene topological insulators, you have to adopt another concept that this saturation number is actually Thomas Fermi screening length divided by the thickness of the cell in the vertical direction. This is a concept, no? So it's and then in this case you know the Thomas Fermi length, and because you know the electric function, the effective mass from various measurements, and so the density. So, and this is the way, and this was applied to silicon and bismuth, and we got to lambda, which are in reasonable agreement with what is known from the literature. So using this number, so we were quite confident it also works for this kind of materials. And okay, then and now these are measurements done here. These are graphene on different substrates, and this also this again already posed a problem because what happens that graphene has a very stiff vibrations inside in internal vibrations within the layer, and the very soft vibrations normal to the plane, so the so-called ZA mode, you know. So which phonons are doing the job, and which temperature you should measure? Well, you should go up to the temperature where you start seeing this is too low as compared to the Debye temperature, for example, is already low. So the question was, how do we work with this data with different copper iridium? So, well, first of all, it was clear that the slope was related to the strength of interaction. And so this interpretation, which permitted us to extract lambda, was based on two different considerations. One, to take the high temperature limit, so because of the high value of the and the other of the vibrations in the optical vibrations of graphene, and the other was to rather to work with the temperature at which the measurement is done physically. And so you see that the response is not very encouraging because we have two different values of lambda, and which differs by a factor which is larger than 2. So this is maybe your factor 2, which you like very much. Maybe there is a factor 2 as well. So you see that we have to take this approach, as we say in Latin, cum grano salis, with certain criticism. But nevertheless, this permitted to extrapolate the single monolayer of graphene, which is higher than all the other, because this was related to the interaction with the substrate. And so we could extrapolate the effect when you have no substrate, just in case you can have. You know that the monolayer, the standing monolayer of graphene cannot exist simply because it's unstable. It's unstable against oscillating surface. Now it's an instability. Unless you block so okay, but this is another argument, we can discuss that. Okay, I have to finish now, and so we have other systems which have been measured here. For example, palladium telluride, and palladium telluride shows also a slope of the Debye-Waller factor of the here it is just intensity plotted, however, on a logarithmic scale, so it's something proportional to the Debye-Waller factor. But you see there are oscillations Okay, you say, okay, the experimental error, you can put just a straight line, as we did, straight line, and we get a value, okay? But the oscillation, now we said, but they are interesting because they occur because you start, when you increase the temperature, you start populating phonons one next to the other, depending on their energy. And when you see some effect, it is because you are populating phonons, which are important for the electron-phonon interaction. For example, and there we put the positions in energy of corresponding energy of phonons 03 or 46, and they are known to be important for the electron-phonon interaction. They're optical phonons. Optical phonons, however, optical phonons are giving an important effect. If there will be only the acoustic one, it will be straight, darker. But if optical phonons come about, then you see oscillations. And these are probably have a physical meaning, despite the fact that the experimental error is still quite large. However, if you use with this lambda, you use the Macmillan formula, you predict the temperature, superconductivity temperature 1.83, which is not in bad disagree, which is in fair agreement with the one we know from palladium telluride. Okay, this is an example of that this kind of measurement can be useful to also for two-dimensional superconductors. Topological insulators, here I showed two other examples in which these values have been derived. It appears that bismuth selenide, which is a Charles density wave system and superconductor, the temperature is as a larger lambda, and this can be related to their electronic structure of the surface. And well, you see that there are nestings, very clear nestings. And this bismuth selenide is a very nice condition because you not only have the Dirac mode, which do not give an important electron-phonon interaction despite many planes. And the reason is that the spins are opposite, and the electrons don't like to make transition between two states which are opposite spins. No, so the interaction is weak. But the important contribution comes from the band states at the surface with the states which are in the other surface states in the accumulation layer at the surface. So these are giving the most important contribution. So this also explains why in a bismuth telluride you have less of that. So this is less important. This was another example. But this gives me the opportunity for a very last thing to praise also the fantastic helium-3 spin echo scattering, which is done instead in Cambridge. They use helium-3, and they use the spin echo. Spin echo means that they have a hexapole, magnet hexapole, in which they wind, in the incident beam, they wind the spins of the nuclear spin of helium, and then they unwind and they exit. And they count how many precessions, which is the difference in the precessions. And this permits to know the change of velocity. And this is extremely precise because the resolution is in the microvolt, the resolution of this technique. And this, for example, bismuth telluride, then it permits to show here, unfortunately, you see that in the dispersion curves on the left, besides the Rayleigh wave, it also shows an acoustical mode, a longitudinal mode indicated L, which has a dramatic drop at a certain point. It has an anomaly. This anomaly is actually related with the nesting. You see on the right side, you see the nesting with the, in this case, it is, yes, it is the Dirac cone, which has there. So the question is, how does the Dirac states produce such a dramatic anomaly? And before I said, well, there is a spin, the spin which is also Is there a mixture with the band states? Do they contribute? Is the spin-orbit interaction, which is strong, active, permitting the electron-phonon coupling through the spin-orbit interaction? This is also possible because the spin is no longer a good quantum number. The good quantum number is the total angular momentum. And as you know, the phonons do have an angular momentum. How much is the angular momentum of phonons? It's very simple. 2 lines are 1. If you have the acoustic phonons, it's clear. The longitudinal is L equals 0. The 2 transverse L plus minus 1. They do have angular momentum. They must. So this is another interesting issue, which is open with this kind of measurements. And okay, this shows in fact the 2 nesting. Tantalum diselenide, which is a brother of niobium diselenide. Well, this helium atom scattering were done in the 80s. In the 80s, in Göttingen, and there was a fantastic thing which was found with helium atom scattering, that the anomaly of the bulk, which is the red arrow that shows the anomaly in the bulk modes, is transferred to 1/2 of the zone at the surface. The surface really way more shows an anomaly. You see a dip, and this is the green arrow shows a dip there, and this corresponds very well to the shift of the nesting in the bulk to the surface. So again, you have an association of the anomalies you see with the nesting at the Fermi surface of the electronic states. So all effects of the electron-phonon interaction, which are elucidated with helium atom scattering. La siguiente shows another effect, the discovery of the charge density wave in tantalum. No, it was not a discovery. The measurement, it was well known, but the measurements of the charge density wave with helium atom scattering, in this case just diffraction, which shows the additional peaks of the charge density wave structures, which permits to measure the critical exponents, which is a classical mythical exponent, 1/3 critical exponents of this kind of 2-dimensional charge density wave. Okay, this just to advertise all the things you can do with helium atom scattering, and also measure the cost lambda here, and it's not so bad. While we measure 0.58, the other calculation gave 49, 0.49. Okay, it's not so bad. Here, now I want just to show that there are fantastic tables with many systems which is measured in this way, 2-dimensional system with the lambda measured with the helium atom scattering as compared to other measurements. And so this is a way to say that over the big number of data, maybe there is some is good, some maybe is not. But however, okay, this is what we know today. You see potassium, rubidium, cesium, barium films, copper, nickel. This is not so bad. It's not so bad. With the saturation numbers, which is basically the depth of the electron-phonon interaction, and so on. Okay, sorry, this is not the time nor the place to study, to look at figure. I just wanted to advertise an advertising paper, which we wrote all together, the initiative of Odile Holst, just saying what you can do with helium atom scattering. This was a recent perspective which has been published. Just to, you see how many things, this is a promise, promise. Okay, you can learn more if you look at this paper. And so I conclude, I wanted just to show, that, so finally first conclusion is we are exploiting an old paradox, which is why the impact electron energy loss spectroscopy does not see valence electrons. The paradox is that neutral atoms interact inelastically with valence electrons, and so it's it was always a competition between these two techniques, which are of course now we know as complementary. With ears you can see things which you cannot see with atoms, and with atoms you can see things which are hard to see with electrons. So these are two perfectly complementary, despite this long dispute. Now we know that we have to use both, if you want to know more. So phonons via electron-phonon interaction, this was the first thing. Also we have observed acoustic surface plasmas, also surface excitations in insulators, and this was fantastic work with the KEV, kilo electron volt atoms, neutral atoms at kilo electron volt. They found a way to accelerate them. They accelerate as ions, so they neutralize, and they make fantastic spectroscopy of high energy excitations. This winter, unfortunately, winter has closed the lab. All are going to retire now, to retirement. Then the spin echo, which I mentioned, slow dynamics, very slow because of the resolution. So you can do diffusion. You can see the diffusion in the K space, and even perhaps magnetic excitations. And finally, other exotic objects like plasmarons and so on. So, okay, this is what I wanted to. So, back to the fishing for Bose-Fermisier. Here I'm with Peter Termes, but the landscape is the one of San Sebastian, maybe you recognize it. And so it's better to be a fisher there. This is fantastic fish. Fantastic fish. And then also now this is an excuse to advertise the book that Peter and I wrote 4 years ago. 3 years ago. And okay. And finally, I conclude saying that new adventures with Otto Stern's invention and a new life for helium atom scattering. So now is Otto is fishing, and so I thank you for your attention. I see that tonight I go back to Donostia, but not by train. This is just the trains which goes to the airport. Thank you for your attention. Sorry, was a few minutes longer.
There are some questions.
One question. This is about the table you showed for Lambda in different materials.
Yes.
The largest one is for lead, I think, not?
One is for?
The largest value for Lambda.
Yes. We found it for
lead.
Lead is large.
Can you show it again? Because you showed the two values. Is that the superconductor material?
Lead.
Yes.
Lead is, yes.
Yeah, no, I mean in the values you showed.
Yes, sure. Lead is a superconductor material. So I think that the best is to go back to the in this way. I think it's this one.
Yes, over there. Yes, yes.
Yeah.
1.55. Which is the meaning of C?
The largest one here is
1.55.
Yeah, sure. Yeah, we find 1.11. Yes, but this is 155. Yes, that's right. Yes.
What is the meaning of C? I mean,
C is a reference which is not shown here. Is the source of is the reference of this word, the value. Yes.
And you also have 1.68.
Yes. In the literature you found whatever you want.
Well, okay, more or less.
Look at the bismuth here. No, bismuth surfaces also has 3. It's not, I didn't report it here because it's not that it was a bit too much. But if you look at the review article by Phil Hoffman on the surfaces of bismuth, there is 3, lambda equal 3. Somebody calculated that, yes.
Well,
that's great. But it's not superconductor. It becomes superconductor only thin layers or nanoparticles, bismuth. Nevertheless, as a respectable lambda, yeah, that's true. And much better than antimony.
How much is antimony?
No, I think antimony, antimony is less. This is 1/2 of bismuth. But antimony is a weak topological insulator, and as a charge density waves, which we could confirm with the spectroscopy, because it was a long-lasting discussion on the charge density wave on antimony 111, and with helium spectroscopy is definitely there. There is a nice diffraction with a critical behavior, so it's an interesting case.
Karma,
thank you for such a nice talk. Actually, I have a related question, if I'm allowed. So today we know that there are ambient temperature superconductors, right? And high pressures.
Yeah.
So, and these are due to the phonons of hydrogen and high anharmonic phonons. And this is extremely efficient to produce superconductivity. My question is of course, the challenge now is to find a mechanism to have such a situation with the ambient pressure. Could you contribute, or do you think that helium scattering can contribute in this?
Well,
in this direction?
this is a question. If experimentalists could invent a machine where you can make a scattering under such a large pressure, because you need an anvil, and the surface is not accessible.
Well, what you need is hydrogen. This is what you need, and
yes,
you need the right phonons. And I wonder if this can be studied in hydrogenated surfaces.
Okay. So just to infer what hydrogen is doing and in a regular normal temperature. Yeah. Well, there somebody was yeah, I don't know, yeah. But hydrogen is a large vibrational frequency. So you probably, and there is still somebody doing with high energy atoms spectroscopy. In France, is Philippe Ronsin.
Yeah, I was going to mention this. That
yeah.
They do the same experiments.
I had a discussion with Philippe because he said, but it's a pity that Winter closed the laboratory just in.
No, but Ronsin can do the same experiments.
Yes, in fact, they're doing it.
In Paris.
I remember perfectly well because I was a referee of two articles, one from Philippe, from two physical review letters, one from Philippe and one from Winter. And of course, I passed both of them. They were saying the same thing, but they came at the same time. So there was no priority question.
Yes, the same issue of
yes. They are two, one next to the other. And somebody should go on with a high energy beam. Because this is important.
High pressure, yes.
The important issue, yes, this one, yes.
With high pressure, you mean really high pressure, yes?
No, I mean the occurrence.
Well, that pressure is giga.
It's not the 1 millibar. You mean high pressure.
And the reason why it becomes superconducting is because of the phonons of hydrogen.
Yeah, the question is the mechanism.
No, but the question is perhaps you can find a model system which could be studied in vacuum. So maybe some complex system with hydrogen, even though we could do this in UHV, but could give some information about the phonon dynamics. So this is a good, interesting point.
Yeah, in the Macmillan equation, hydrogen provides a fantastic prefactor, fantastic frequency. But the question is lambda. The question is lambda. So if lambda is reasonable, maybe you can be displaying. If it is BCS, because the question is also, is it BCS?
Did you try to measure VSCO or some other high critical temperature superconductors?
No, there was, this is a, no. They didn't think of that at the time because the VSCO and IPCO were in the lab of Peter, and it was this strange.
I think the point was, as far as I know, is that this is also a very interesting point that at that time samples were not good enough. I mean, the small letter in the contract is we need excellent and big samples for this.
No, the samples of this one is
So
very
but
good.
today maybe if you can find samples which are big macroscopically and high quality, perhaps it can be easier.
The sample of IPCO were good because the diffraction came out good, but they simply didn't think of measure through the transition temperature, which IPCO was about more than 77, was about the nitrogen. So they were diffraction this temperature, another diffraction, another temperature, but they didn't go through. And so I said, but it's a pity because the measurements are there, but they're useless.
You could think about repeating this with IFCO, maybe, yes.
Yeah, I mean, it was not yet the idea of doing these things. But Tantrum, the science showed our measurements in the 80s. And the surface was good because you see this beautiful charge density wave.
The oxides, the high temperature oxides, the ones that are developed in Gushikon, basically. Yes.
Yeah.
Or this family of materials.
Yeah, the cuprates.
Cuprates, yes, cuprates.
But in VISCO, there are very nice samples and they are very big.
That's a nice idea.
Yeah, this is.
So there are more questions. Yes, yeah. You please.
This may be a naive question since I'm in this field, but I'm aware that there are now researchers that are able to suspend graphene layers and other kind of 2D materials. Is there any fundamental reasons that you cannot use this technique for these suspended membranes, and you can access the electron-phonon in bare graphene?
Well, no. Your metal scattering could be if you can suspend the graphene.
Since I'm asking since the electron-phonon goes down when you reduce the number of.
Well, according to that extrapolation should go up. But the question is, the ideal flat structure is unstable, which means that it undulates. The reason is that there is a common strange thing that there are people saying that there is a parabolic dispersion curves of the ZA mode. This is impossible. It is there is a famous theorem already. If you calculate with just the mean square displacement with the square displacement, this is diverging even at 0 temperature. So this system cannot exist. So they say parabolic, but cannot exist. The reason is that there is a confusion between the transverse mode and the flexural modes. They are two different things. And this has been explained already by Lagrange and by, Lagrange, yes, and Sophie Germain, famous mathematician, in her thesis, that because they were studying the oscillations of bars, of flat bars and of roofs, in the constructions. In the case in which the roof is blocked at the boundary, or in the case it's free. So it is different between the transverse mode if it is the boundaries are free or if they're blocked, or the boundary conditions. They're different. Why that? Because when you move in this way, you shorten the distance, and therefore that is not constant for the flexural modes. So this is the big confusion that exists about graphene vibrations. And the instability, if you try to build with without blocking, the singular are undulating, are unstable. They go into. This has, of course, an influence on the electron-phonon interaction because you change dramatically the spectrum in the low energy part. If the electron-phonon interaction originates from the highest mode, as it seems the case, because it seems that the most important one is a longitudinal optical mode at the K point. This is the largest anomaly, so is in that case, it doesn't matter. Can you make an experiment with the
I
suspended
think the
graphene?
challenge is to make a sample like this, a suspended graphene, which is big. Big means say millimeters. So then you fix it and the borders, then it should be possible to see this vibration.
Yeah, this would be. I mean, like you have a hole, no? You have a substrate with a hole, then you.
It's
you
several
deposit
holes.
it,
This
yes.
is a possibility. Yes.
Yeah.
Sample with several big holes, so periodic holes, and then you put a graphene on top of, for instance,
So your next,
graphene, where you know that it sticks. So we have an idea about it.
your next
Someone has to
experiment,
make the
yes.
sample. That's it. I can mention once I get the sample. To produce a sample is okay, additional extra work. I don't know if there are, Ivan, if you're there, if there are questions from the people connected online, or
Yeah, I mean, people from the audience can make questions if you want also. So you are, in principle, allowed to unmute. So any question from the audience, online audience? No, I think not. There are not questions from the audience.
okay, then thank you, Ivan. Thank you. We thank Giorgio again.